super quick bio, see whatever I remember. So Dave got his Bachelor of Science from the University of California, Santa Barbara in honors in geosciences, his master's and PhD from the University of Arizona, got to live in Tucson, also in geosciences, worked as a consulting geologist down deep in the boreholes, looking at landslides and other fun things in Southern California.
And faults.
Currently is associate professor at Idaho State University, where he teaches basically almost every class they have. Main interests are in structural geology, geochronology, and take it away. Are you okay?
Yeah, everything is right except I'm not an associate professor.
Oh, okay.
Assistant professor.
Assistant, I'm
So
sorry.
hopefully
Tenure.
eventually will be.
Tenure.
Just a minor detail. Well, thanks everyone for coming. I decided upon Mike's suggestion to give a little summary of my talk from last night and expand a couple things. It's going to be much shorter than last night, but I'll expand a couple things and kind of emphasize the take-home points from that talk, and we can have some discussion about it if you guys are interested. And then after that, I'm going to talk a little bit about the basin and range, and in particular the basin and range in the Northern Rockies. To be honest with you, I don't know a lot about the basin and range around here in particular, but I know a lot of regional stuff, so we can have some discussion about that. So what I talked about, so most people were there last night. A couple of people that weren't. I basically, I need to acknowledge my collaborators and students and funding as shown here. And the takeaway from my talk is that there is, what I argue is that if you look at the regional scale picture of North America, and if you look at the same kind of thing in South America, there are some really clear correlations between the style of thrusting in the fold and thrust belt and the architecture of, this is the upper plate in a convergent subduction zone system. And in the style of deformation, basically the takeaway is that it's very much related to the ancestral history of the plate that's involved in the deformation. And so you can see that from first order if you just zoom out and look at Western North America. If you look at the distribution of passive margin deposits on the western side of North America, and you look at the distribution, and it's kind of a really light gray shown in here, but these dark black thrusts, you can see that the distribution of those thrusts, which is, I'll talk about in a second, is what I'm calling thin skin deformation. That's kind of your standard fold thrust belt style of deformation. You can see they match very, very well. And so it speaks to first order that the thrust belt, the geometry of the thrust belt, so where it's located along the margin, is intimately related to the pre-existing stratigraphy at the margin. And this is something that people have known for a long time. But I'm mainly interested in understanding why that's the case, and in particular, why there's all these changes, more detailed changes in the geometry of the fold thrust belt, and why there's a transition both along strike, so parallel to some of these thrusts up here, and perpendicular to strike. So if we're going perpendicular to these thrusts, going out farther toward the east into the continental interior, why that transition happened. And I talked last night in much more detail about some of the ideas about why that happened, and I'm going to kind of clarify that story for you. I wanted to point out, I don't think I did a very good job last night of defining what salience and recesses are, or reentrance. And so these are terms that refer to areas, salience in particular. They refer to where the thrust belt extends farther out into the continental interior relative to other places. And so this down here, where this kind of has this bow and arrow shape, that's called the Wyoming salient. And this up here, where it has another kind of eastward, convex shape toward the continental interior, that's called the Helena salient. And these two salients are separated by something in southwest Montana we call the Southwest Montana reentrant. And so that's an area where the thrust belt curves back toward the interior of the mountain belt. And then this down here, similarly at the southern end of the Wyoming salient, we call this the Uinta reentrant, and that's where the thrust belt continues farther back toward the interior of the mountain range. So I'm interested in understanding why these form, what controls the shapes of those, and what controls the transition from this particular style of thrusting to these thrusts that's known as the Laramide province that's farther to the east. And so what I talked about a little bit last night is that this is kind of your standard view of what a full thrust belt looks like in cross-section. This is what it looks like in western Montana. Wedge-shaped, we'd say it tapers toward the right or toward the east in this example. The basement is not involved in deformation. There's a bunch of relatively thin thrust sheets that are just progressively stacked on top of each other. We call this an imbricate thrust system, so you guys probably know about imbricated class in the river. This is very similar to that. And that looks similar to what we have if we were to draw a cross-section from southeastern Idaho to west central Wyoming. You'd see that relatively thin thrust sheets stacked on top of each other, all dipping toward the left of the interior and detached from the basement. And this is very different than what people call the Laramide full thrust belt, which involves basement thrust dipping, oftentimes many different directions. There's not nearly as much shortening accommodated in those. And they oftentimes, especially in South America, they involve reactivation of older weaknesses in the crust. And so here's a little bit different view than what I gave yesterday, but this was a study that my co-authors and I, we were trying to understand in South America. So here's the big, here's the Andes, here's Argentina, here's Bolivia. There's a border between the two. We were trying to understand what controls the change in the geometry of the thrust belt and the structural style. Down here, there's all these thrusts that are in mountain ranges. This is called the Sierras Pampeanas. And all these mountain ranges are kind of spaced far apart. They're much farther out in front of the main part of the thrust belt, farther from the plate boundary, in fact. And we're trying to figure out why, what some of the main factors were that were controlling that. So what we did is we compiled actually hundreds of cross-sections that were drawn by other various authors across the frontal part of the full thrust belt. And what we did is we connected up, so here would be a cross-section drawn, so G, that would be up here in western Bolivia. This H would be down here in southern Bolivia. I would be down here and right at the border between Bolivia and Argentina. J down farther to the south, right there. K down here, kind of in the central part of Argentina. And what we did is we wanted to look at this thrust belt in a different view, and this is kind of a mind tease. But if you can imagine drawing a cross-section and connecting up all of these existing cross-sections, drawing the cross-section parallel to the mountain range. And so that's what we did. We call this an along strike cross-section. And what our goal was to see how, at the very frontal part of the mountain range, how the thrusting changes and how that relates to the stratigraphic framework of the mountain range. So what we did, this is what we did down here. It has a vertical exaggeration because it's a huge, long, thousands of kilometers long cross-section. 7,000 kilometers. This is just the southern portion of South America. We did all the way up to the northern end of South America. And what we saw is that to the north, so looking at G, H, I, you can see G, H, and I, there's generally relatively undeformed stratigraphic section where those cross sections are drawn at the frontal part of the full thrust belt. So undeformed stratigraphic section. Whereas farther to the south, you see that this same stratigraphy does not continue. And in fact, there's very little stratigraphy within this region right here that we call the Transpampean Arch. And this correlates with the transition to where you start to get this different style of deformation. And so here you can see this is drawn across J right here in northern Argentina. You can see that this gray is basement on here. There's two different shades of gray, and the details don't matter at this point. But you can see that the thrusts in here, they're dipping the opposite direction. This one reactivates an older Cretaceous fault, a Cretaceous normal fault. And as you go farther to the south, you see a similar similar observation, relatively thin basinal stratigraphy and involvement of basement within the thrust faults and dips in different directions. And so we thought that this observation, something about the orogenic architecture was controlling the change in the style of thrusting. Yeah,
I'm assuming that all the force for the thrust is coming from out along the coast.
yeah.
I'm surprised it can transfer so far.
Yeah, it can transfer very far from the coastline, and that's a good transition into what some of the early ideas were for why it translated so far out to the east. And I talked about this a little bit yesterday, but one of the early observations, so you guys may have heard of the Wadati-Benioff zone. So it's a feature in structural or tectonics, plate tectonics, where there are a couple of scientists that noticed that you can trace the locations of earthquakes at subduction zones and try and define the geometry of the subducting plate down beneath the overriding plate. And so basically, geophysicists started to recognize that in this area down here in central Argentina, the subducting plate was shallower, had a shallower subduction angle than elsewhere along the margin. And so it wasn't very well defined. This is pretty coarse scale. It's mostly the work of Isaacs, that original geophysical work. But you can see that what they did is they hypothesized that there's a spatial correlation between this angle of shallow subduction. So where there's shallow subduction, they hypothesized that that is the cause of this particular style of deformation in the upper plate. So they took this and they said, okay, look at North America. It looks like these are very similar. We hypothesized that there was an ancient shallowly subducting slab beneath North America that caused this eastward migration in the location of deformation and activation of this different structural style where these thrusts are irregularly oriented, they're involving basement, and so on and so forth. So here's kind of the view, a cartoon, simplified view of how that might work, and I don't have references from DeSalle and others, 2009. But they hypothesized that there was normal subduction until about 80 million years ago. And that was followed by a shallowing angle of the subducting slab. And they hypothesized that this shallow subduction angle actually resulted in that deformation being pushed farther into the continental interior. And so that was, we could think of this thick-skinned structural style as a signature of shallow subduction. So that was their hypothesis. And I will say, I think that there's a lot of merit and a lot of evidence that there was shallow subduction, that there is shallow subduction right now in South America. I'll talk about that right now. And I also think that there's good evidence that there was shallow subduction beneath Western North America as well. But my point last night was to show that I don't think that's the fundamental control on the style of deformation. I think a cause and effect of shallow subduction and this structural style, those are not necessarily linked together. And so I'll hope to expand that in more detail. So, and this was part of the reason why I think they're not cause and effect. And this reason is because, so these are actually, I didn't point this out last night, but these are contours of the subducting slab. So you can see that these right here, so it's, I think this is, so 80 kilometers or whatever this is, maybe 90 kilometers, 90 kilometer depth, 100 kilometers, 125, 150. And so the point is that up here, it's relatively constant slope, relatively steep dip. Whereas when you go to the south, you can see that there's this, just like a topographic map, you can see that there's essentially a ridge, relatively high elevation area of the subducting slab. And the point why I show this is that you can compare the geometry of this subducting slab shown here in three-dimensional view. You can compare that to what the original hypothesized extent of the shallowly subducting slab was, and you see that this is very narrow. This is only a couple hundred kilometers narrow, whereas the original hypothesis suggested this is upwards of 1,000 kilometer wide segment of shallow subduction. So what I think an important observation from this more recent data is that the active deformation that's happening up here, that involves thick skin deformation, basement involved thrust, I don't think you can attribute that to the shallow subduction angle because it's so far away. And so I think there's alternate factors that are controlling the structural style. And so, and I'll talk a little bit more about that. But I just wanted to, there's several examples that I gave yesterday and about why, other areas around the world, why shallow subduction can definitely not be called upon to generate this thick-skinned style of deformation. And an easy place to do it is in the India-Asia collision zone. What you see is that there's areas, so getting back to one of the early questions, there's a whole area inboard here that doesn't deform at all. So that's kind of interesting. Why does that happen? People think that there's probably some strong basement feature within the crust that doesn't like to deform. And instead, deformation is propagated out into here, and this is the Tian Shan. And there are many thick-skinned basement-involved structures in the Tian Shan that are thousands of kilometers away from the collisional plate boundary, and we don't think that there's any subducting plate underneath that part of Asia. So it's a reasonable example that suggests that shallow subduction is not the main factor that controls the style of deformation. So I'm just going to summarize what I said yesterday right here as well, but I talked about two things. Why is the Wyoming salient, why does it have this shape? Why is it curved out toward the east? And then the second thing I talked about is why is there this transition, I just talked about shallow subduction, why is there a transition toward the continental interior for this different style of deformation? So the first one, I'll just reiterate what I said here, and one of the primary observations that we made is that most of the Wyoming salient, the basal level that the thrusts are detached on, so in other words, so if you look at this cross section right here, this stratigraphic level right here, that's all this Cambrian, this weak Cambrian shale, the Grovant shale, and so there's within the Wyoming salient, it seems like all of the thrusts root down into that weak shale. But if you go away from the Wyoming salient, so in the Uinta reentrant or the Southwest Montana reentrant, you see that it does not actually, the thrust belt does not utilize that weak Cambrian shale horizon. I think that's telling us something about why there's this shape in the full thrust belt. And so the first area that I go to is in east central Idaho, where you see, interestingly, is that the Ordovician rocks are directly on top. So 450 million year old rocks are right on top of the belt supergroup, which is 1.4 billion years old. So there's a huge unconformity, a billion year old unconformity between those two types, those two rocks. And what the important thing is in here is that there's no Cambrian shales deposited in central Idaho. So I hypothesize that this is the reason why the northern end of the Wyoming salient occurs there, because there were no efficient shales for the thrust belt to glide upon. And then I also went down to the southern end in the Uintas, and we made the observation that over here in the west, you see the Cambrian rocks directly on top of the older rocks of just a continuous stratigraphic succession from 750 million years over to 500 million years, and all the way up through the section essentially. But if you go farther to the east, what you see, this is into the Uintas, what you see is that there's an unconformity between the Madison, which is Mississippian, and so 350 million year old rocks and 750 million year old rocks. So there's an unconformity between the two. And what I hypothesize, the important thing about that unconformity is it removed that efficient shale horizon that much of the full thrust belt used within the Wyoming salient to glide upon. So I suggest that at both ends of the Wyoming salient, the reason why it's shaped like this is essentially, you can think of the thrust belt just gliding along easily. It's relatively low coefficient of friction along the base of the thrust belt, and so it slides relatively easily toward the east. But on either side, it is not able to glide along that same detachment horizon, so it maintains this curvature that's related to the original distribution of that Cambrian, that weak Cambrian shale that it was sliding on.
And I noticed because the Cambrian shale has been eroded off of there, it was deposited there.
In the south, yeah, it was deposited there in the south, but it was not deposited in east central Idaho. So
it was eroded off to the south of the salient.
Yeah, exactly. So
prior to the Cretaceous
Exactly.
garage.
And
Yeah.
it appears that according to the cross sections, that the depth of the basement rock, the salient is much deeper than to the north and to the south. I assume that corresponds to the preservation of the stratigraphic record.
Yeah, and so so one of the early hypotheses for the shape of the Wyoming salient, and I talked about this in more detail last night, but one of the early hypotheses was basin thickness, and in particular Paleozoic basin thickness. And so they said, look, the Paleozoic section, so rocks that are younger than 540 million years old, and that's just an arbitrary cutoff, and that's what I'm going to emphasize in a second. They say that the thickness of the Paleozoic section corresponds to the shape of the thrust belt in here. But it turns out, and this is a point I made last night, it turns out that the thickest sedimentary basin in North America is actually located right here, the belt supergroup, over 15 kilometers thick. So I think that, sure, if you say that it's a Paleozoic stratigraphy that's correlating with the shape of the full thrust belt, then maybe that correlation does work, but it's not necessarily basin thickness. It has something beyond basin thickness that's controlling the shape of the full thrust belt. Yeah.
Dave, do you think those detachment layers are the cause or the result of those thrust springs?
I'm not sure I understand the question.
Well,
if you rephrase it?
So what's causing those detachment layers, right? Why are they there? Are they there as the result of the thrusts themselves, or are they there before they cause those thrust layers?
So like the Cambrian Grove Arm
Yeah.
Shale. Yeah, so what I'm saying, and and this is going to be a conclusion at the end of this summary, is that the history that long predates formation of this thrust belt here. So, for example, deposition of the 540 million year old shales, or erosion of those, which happened in the Uinta example that happened about 350 million years ago. Those events that led to preservation or non-preservation of those shales, that's ultimately what controlled the shape of the full thrust belt. And so I think the same thing is true in South America. And what you see in South America is this big regional mountain building event that was there, that took place in Ordovician times about 450 million years ago. And what that did is it created a big topographic high, and there's a lot of rocks that were deposited to the north, but no rocks that were deposited on that topographic high. And what I think is important here is that even though there is a thick section of sedimentary rocks within this high right here, they were previously deformed during this 450 million year old mountain building event. So that resulted in a lack of preservation of any efficient detachment horizons like were utilized in this portion of the full thrust belt. I think I said that in a little bit too complicated of a way. But what I'm basically saying is that this, here's a Devonian paleogeographic map. There's really weak shales that the thrust belt utilizes in Bolivia that correlates to this thin-skinned style of deformation in the full thrust belt, but those are not present farther to the south. So I think that, again, an event that long predated formation of the Andes, so the Andes really only formed in the last 40 million years, but something that happened 450 million years ago was ultimately the reason why the thrust belt has its modern shape.
So can you comment on the amount of shortening between the salients and the reentrance?
Yeah,
Does it balance out?
No, it does not balance out. There's substantially more shortening in the salients than there is in the reentrance. And so if you look here in North America, so you see, so here, this is 105 kilometers, shortening decreases in magnitude as you go toward the boundary of the salient. And it's true in South America too. So if you look at, if I have a good, so if you look, so this is fundamentally a salient right here too. They call it in South America, they call it an orocline, which is just kind of a bend in the shape of the mountains, but it's basically the same thing as a salient. And what you see up in here is there's about 350 kilometers of shortening, but when you go down farther to the south over here where you start getting this thick-skinned style of deformation, it's closer to 140 kilometers. So a substantial change in the magnitude of shortening. So these rocks, basically they don't like to be shortened. And these rocks in here, they can accommodate shortening very efficiently.
And the coastline is reflecting that.
Yeah, the coastline follows the curvature in the orocline. So a lot of people have thought about that problem.
Do we see that in North America?
I don't know. I think it would be tough to know because of all the terrains that have been stacked on and the subsequent translation of those terrains. But possibly you do see it. I'm not sure. It's a good question. All right. And so what a point I wanted to make is that in the absence of these of those detachment horizons, so in Bolivia, which is shown right here, in the absence of those detachment horizons, which are in essentially 450 million year old rocks and 400 million year old rocks, those are, what happens with the thrust belt is what it does is reactivates these older rift faults that were related to the opening of the Atlantic Ocean. And so I think that in these salients where there are these detachment horizons, the thrusts are utilizing these weak sedimentary bedding planes. So they like to reactivate weaknesses. They prefer to do that rather than forming new faults. And in the absence of those sedimentary bedding planes, what they do is they instead reactivate some older weaknesses that are also present, but not sedimentary bedding planes. Instead, there are pre-existing faults and fractures in the crust. So I think that there's not really that much of a difference. There's a difference in the geometry of these thin-skinned and thick-skinned fold thrust belts, but they both do the same thing. They don't want to form new faults. They always reactivate existing weaknesses, whether it's stratigraphic layers or whether it's pre-existing faults or various other things. So I don't think they're too different from one another. And so these were my main takeaways from looking at the Central Andes and the Northern Rockies, is that all thrust belts generally propagate into the continental interior. So that's something we all know. So they get younger. All the thrust faults on the right side here are younger generally than the thrust faults on the left side. So at first, given that most continents were attached to another continent at some time, rifted apart, lots of sedimentation formed on those passive margins. So there was a big passive margin succession on many of these continents. At first, the thrust belt, which is developing at the margin, is starting to interact with that pre-existing stratigraphy, and so the thrust belt is likely to form within that pre-existing stratigraphy. But as you propagate the thrust front toward the continental interior, you no longer are going to have those stratigraphic detachment horizons to utilize within the full thrust belt, and instead what it's going to do is reactivate existing basement weaknesses. And so generally as you get toward the continental interiors, and this is why the title of my talk is crust, mountain building and old continental crust. Old continental crust has a lot of pre-existing weaknesses in it. It's had a long, protracted deformational history. So I think old continental crust is likely to deform in a totally different style than when you have this pre-existing layer cake stratigraphy with all these weak detachment horizons that you can utilize. And I told you that I think that there's good evidence that shallow subduction is occurring in South America and did occur in North America. And I think there actually might be a link between the style of deformation in the upper plate and the subduction angle, but I don't think it's cause and effect. I think that shallow subduction may enhance the deformation of the upper plate, which could promote propagation of the thrust belt farther into the continental interior. But it's not really because there's this cause and effect linkage that the shallow subduction somehow creates this magically different style of deformation. It's that the thrust belt just isn't able to accommodate as much shortening in the interior part, and it needs to propagate farther into the continental interior. And when it does so, it'll reactivate these pre-existing basement weaknesses. And the point I wanted to make, and I'm not sure I did a good job of it yesterday, but I think that this thick skin deformation, I think there's good evidence that this thick skin deformation would have happened in North America. I think it did in southwest Montana, completely in the absence of shallow subduction. So I think it's a natural progression, with just a normal dip to the subducting plate, that the mountain belts have this particular geometry in the absence of these weak sedimentary layers to activate the thrust with it. So I have a little schematic. So actually,
that was because of the age of those deformations in southwest Montana.
Yes, they're
That
older.
They predated.
Yeah. And so that's kind of what I have a couple slides that put it here at the end that were not things I put in before. And so actually, this is, these ideas are the intellectual merit for a proposal that was just funded through NSF that's seeking to understand whether this is a viable hypothesis, basically. And what we're going to do, so this is a figure from the proposal, but what you can see is that, so these are cross sections, so undeformed, so prior to deformation. And I know it's kind of hard to see, but the point here I want to show you is that there's relatively thick succession that includes rocks that are all the way from 750 to 300 million years old. The complete passive margin succession, just like we have in westernmost Wyoming. That's present here in the west and central Idaho. However, when you go farther to the east and you get on top of this feature that I called the Lemhi Arch previously, what you have a complete absence of those 750 to 450 million year old rocks, and instead you have those 450 million year old Ordovician rocks sitting right on top of this 1.4 billion year old quartzites of the Belt Basin. And so what I hypothesized is that in central Idaho, you started to develop thin skin thrusting along these weak detachment layers, but as it approached the central part of the Lemhi Arch, it didn't have those weak detachment layers in the central part in here. Instead, what it did is it started to activate the brittle ductile transition, or something similar, possibly another weakness in the lower part of the crust, which acted as a weak detachment layer to translate deformation farther to these thick-skinned structures in southwestern Montana. So I think this is because I think it translated this deformation farther into southwestern Montana because it didn't have any of these weak detachment horizons to utilize in east central Idaho. So that's kind of the more detailed summary of what I was trying to accomplish last night. And let's see.
The dotted lines are old faults in your cartoon.
These are just faults that haven't yet been activated, but then now they have been activated. So this doesn't show fully which the modern day view. This is just a snapshot from 90 to 80 million years. And so what our preliminary data show is that these structures in the interior part of the thrust belt were active at about 100 million years old, and the next most recent activity occurred on one of these thick-skinned structures that's called the Blacktail Snowcrest uplift in southwest Montana.
And the faults between the two were not reactivated for some reason.
No, well they were formed later on.
Okay.
So the thrust belt is continuing over here. It jumps out over here, and then it continues to deform in the interior part of here. But the thrusts have this different style, so it's not like these thrusts that have formed in central Idaho. Any questions about that? Let's see. And I gave you guys some speculations last night at dinner, and I'll just put it in here as food for thought. But what I find interesting is that these areas that are hypothesized to have had shallow subduction both occur at the transitions from where you have these detachment horizons for where you don't, where you have this thin skin deformation to where you have this thick skin deformation. And so I say I'm flipping the script. Possibly there's a factor, the ability of the upper plate to deform, whether it can easily deform where you have these weak detachment horizons form this thin skin thrust belt and accommodate a lot of shortening, where it can easily deform, it's not likely to form a shallowly subducting slab. But where it can't easily deform, perhaps it actually impinges on the downgoing plate and causes the slab to shallow. So this is kind of a totally arm-waving idea. And there are other people that have speculated. Rick Allmendinger in 1983 suggested something along these lines, and another author named Jonas Clyde suggested this in 1999. But I think that it's possible that some factors of the overriding plate could affect big picture geodynamic things at the plate interface. And so here's kind of the The most recent view, this is from Yankee and Weil 2015, and this one right here is Salience 2003, that show kind of what our modern view is of how the laramide orogeny occurred. And I do this in quotes because I don't think that these are fundamentally different orogenies. They're the same orogeny, and I think we can't define these structural styles as their own orogenies, because if they formed independent of something like an episode of shallow subduction, then they are literally the same orogenic event as previously. But the modern view is that there was a subducted oceanic plateau that continued into essentially southern Utah and into Colorado and eastern Wyoming. And this is what was hypothesized to result in a shallow angle of subduction, and they call it a segmented shallow regional subduction. So there would be a corridor of shallow subduction that occurred in this area. And the reason why they define it there is because of the magmatic arc in the Sierra Nevadas that ceased to be active at that time. So this is kind of the modern view. And so like I said, if the structural style is not a signature of shallow subduction, maybe we can flip the script and say that it's actually the rigid upper plate that's resulting in the transition to shallow subduction. So that's all I have for summarizing that talk from last night. I hope it made it a little more clear kind of what I was trying to get across. Do you guys have any questions about that?
You raise questions. How do the absoricas, which are supposed to be the result of a subduction zone, work into this, because they're about this age?
Well, so where are the absoricas on this map?
They would be in northwestern Wyoming. Yeah.
Well, so are the absoricas? I'm showing my limited knowledge of western Wyoming geology, but are the absoricas? They're within what we call the thin skin portion of the full thrust belt. Is that correct?
Their volcanic range,
Are
equivalent to
you
the
thinking
Cascades.
of the volcanic origin?
Yeah.
Okay. Yeah. So what the paradigm is that there was a shallowly subducting plate, and as it started to steepen after this oceanic plateau passed beneath here, it started to steepen, and that because there's kind of a characteristic depth above these subducting slabs. So this is where there's dehydration that comes up here, melts the mantle, and that forms these volcanic arcs. If the location that slab is getting to that depth is farther inboard in the continent, it's actually going to be, it's going to be, there's going to be magnetism farther inboard, and as that slab kind of peels back from the overriding plate, then that location of magnetism would make its way farther to the southwest. So that's there's Eocene volcanic rocks in Idaho too. They're called the Chalice volcanic group, and there's Eocene volcanic rocks near Dillon that are called the Dillon volcanics, and those are hypothesized, and those are kind of poorly understood, but those are hypothesized to be kind of the northern limit of where that, what they call rollback magnetism, where that started. And so the modern view, I believe, would say that the Absarica volcanics are a result of that rollback magnetism after shallow subduction. But what I think is pretty interesting, and it kind of drives home one of the points I'm trying to make, is that if you look in southwest Montana, east central Idaho, and northwestern Wyoming, it's pretty far from the boundary of where the shallowly subducting slab was supposed to be. So, possibly there's some boundary effects from that shallow slab where it transitions into a steeper plate boundary, or maybe there's something else happening. In Eocene time, people think that's when there started to be significant extension of the crust in North America, and so maybe they're related to extension. But still an open research question, I would say.
Thank you.
Any other questions? So how long are we supposed to go to?
Well, we have room till 2 o'clock, but you don't have to go till 2 o'clock.
All right, so I'm going to transition into something that's pretty different, and this might be, components of this might be, it's kind of all over the map in terms of the level of complexity. So I hope I can kind of keep it on at the right level. But I'm not a seismologist. I'll say that from the beginning. So, how earthquakes work, I generally know how they work, but the details of it, I am definitely not an expert about. And, seismic hazards and earthquake shaking, structural engineering, that is definitely far from my expertise. But understanding where the active faults are and understanding the evolution of the basin and range, I can start contributing to that discussion. So that's what I'm going to talk about now. So if you guys have questions, you're welcome to chime in.
Looks like we're in the very high frequency.
Yeah. So this is a map that I like to show in Idaho because you guys probably know here that there's a big active normal fault adjacent to the Tetons, but in eastern Idaho, people have no idea really that there's a likelihood of big earthquakes happening in that part of the world. So I like to show this map from FEMA that shows there's the highest probability, the same as much of California, for frequency of shaking that could cause damage. So it's kind of a wake you up right off the bat. All right, so basin and range extension. So I like this view. This is Bill Dickinson's view from 2006 summary paper. I like this view of basin and range extension because it kind of gets away from labeling all these different provinces in different ways and kind of just says, look, all of this area right in here shown in orange, yellow, and orange down here, as well as the Rio Grande Rift, those are all areas of active extension happening in Western North America right now that are essentially a continuous tectonic province. And so the point is there's a huge area that's undergoing extension right now, and we call this the basin and range. We think the basin and range occurred for a couple reasons, but essentially right now, and this is kind of a complicated geodynamicist view of why it's occurring, but what this diagram shows are the stress directions within the western part of North America, and this is from a bunch of borehole data. So strain gauges inside of boreholes, and they can see the deformation of those, and they can infer what the regional stress directions are. And what you can see is that there's generally an east-west extension direction, basically, is what this map is showing. And what these authors attribute this extension to is the high elevations in the western part of North America. So, in a complicated way, they call it gravitational potential energy. But in other words, the crust was really thick, and there was a subducting plate over here, lots of horizontal stress propping it up. And when you transition that plate boundary into a strike slip plate boundary, it all kind of starts collapsing toward the west. And so that's kind of what they think mainly is going on. They also think there's a contribution of the Mid-Atlantic Ridge to this extension in here, and I bring that up as people that have taken an introductory plate tectonics course, they teach you two things about how plate tectonics works, what the drivers are. They talk about slab pull, which is that there's these subduction zones and this really dense slab that's kind of yanking on this other plate that's pulling down behind it. So that's one of the things they think drives plate tectonics. And they also think that ridge push, so this lower density material beneath these mid-ocean ridges, divergent plate boundaries, is actually propping it up a little bit and it's kind of sliding away from that. So ridge push and slab pull are some of the main factors driving plate tectonics. And here we think that it's mainly for the basin and range, mainly gravitational potential energy that's driving extension, but there's also a contribution from extension in the Mid-Atlantic Ridge, which is pretty original. Yeah.
Is it also possible, I've heard it hypothesized, that part of the extensional forces are also coming because when North America overrode the spreading centers, then the Pacific plate is now moving to the northwest, and so it is, in a sense, pulling North America as well, and contributing to that extension.
There's definitely a contribution. I'm going to show some figures that show it in a second. There's definitely a contribution to the trajectories of materials. So if you look at the displacement directions on faults, there's definitely a contribution from the San Andreas fault system and the spreading center, especially in the western side. But over here, so you can see there's a deflection as you get farther closer to the San Andreas fault system. There's a deflection. They become more northwest oriented. But in here, I don't think people think that's related so much to that as the gravitational potential energy and kind of collapse to the west. So these are some animations from Tanya Atwater, who was actually my plate tectonics professor when I was an undergraduate. But she put together these really cool animations that show the evolution of the basin and range as the spreading center started to interact with the plate boundary. So you can see, I'll play this again, but you can see as the spreading center started to interact with the subduction zone and form a big transformed plate boundary connecting this portion of the spreading center down with this part down here, you started to get a lot of the extension within the basin and range. And so fundamentally, there's the transition in the plate tectonic regime was a big factor in controlling why it started extending after it was a big mountain belt. So you can see here, California and Nevada are really thin. Idaho looks kind of funky. And then at about 15 million years ago, extension really starts to take off in much of the basin and range. Here's another view from Falls and Henry that shows kind of the same thing. And what you see is that at about 15 million years ago, much of the modern extent of the basin and range has started to initiate. And then at about 12 million years ago and 5 million years ago, it starts to propagate into eastern Idaho and into southwestern Montana and western Wyoming. So this is a modern view of the extent of basin and range extension.
And it's also in Yellowstone.
Yeah, I'm gonna talk about that in a second. So I like this quote from Clarence Dutton, who was a USGS geologist, that the basin and range looks like an army of caterpillars marching toward Mexico. Yeah, or the opposite direction. Yeah. But fundamentally, all the topography in western, at least over here in Nevada and Utah, eastern California, eastern Idaho, pretty much western Montana, all of that topography is controlled by basin and range extension. And each one of these little caterpillars is a mountain range that's been uplifted in the footwall of a normal fault. So here's a normal fault right here. This side is slipping down relative to this side right here. So you form these basins and ranges. And so this is fundamentally what the basin and range looks like. If we look at a couple views on what's happening, a modern snapshot of what's happening in the basin and range, you can see, so these are all, people call them Beachball diagrams. You can see that there's two main locations. So these are where the biggest earthquakes are occurring within the basin and range. And these are telling us what type of earthquakes are occurring. We'll talk about that in a second. But there's basically two areas where the earthquakes are occurring. Over here along the Wasatch Fault Zone, and over here on the eastern side of the Sierra Nevadas, which is what we call the Walker Lane or Eastern California Shear Zone. We'll talk about that more in a second. And just to give you a refresher of what these Beachball diagrams mean, essentially during an earthquake, there's different seismic stations around the Earth are feeling a little bit of a push relative to which side went toward them. So either they're a normal fault, one side slipped down, or they're a thrust fault or a reverse fault, one side slipped up. But depending on what the relationship is to which side went up versus which side went down, they either get a little bit of a push toward them or they get a little bit of a pull toward the earthquake. And it turns out you can map all of this around from the seismic stations, and you can come up with the areas that got a push and the areas that got a pull, and you can plot out what these little circles. You can plot out these little circles, and they tell you something about the type of earthquake that it was. And so these ones right here, the ones that have these two perpendicular lines in the middle, those are a strike-slip focal mechanism. These are called focal mechanisms. These right here with the white in the middle and the dark on the outside, those are called normal fault focal mechanisms. These ones with the dark in the middle, those are reverse fault or thrust fault focal mechanisms. So you can look at the distribution of those different beach balls and learn something about the types of earthquakes that are occurring. So going back to this map right here, you can see that most of the earthquakes in, let's say, along the eastern part of the basin and range, what kind of earthquakes are those?
Strike.
There's one big strike slip fault in there, a couple down there. Most of these in here are actually normal because they have that white part in the middle. But if you look down over here with this adjacent to the San Andreas Fault, what kind of fault mechanism are those? Yeah, those are all strike slip faults. And then over here in the western part of the basement range, we kind of have a mixture. We have these, some of them that are normal fault focal mechanisms, and some of them that are strike slip focal mechanisms. And so this is telling us something about the type of slip that's occurring along those faults. So here in the San Andreas Fault, it makes a lot of sense. It's a big strike slip fault system. There are strike slip faults, strike slip fault earthquakes happening over here. In the Wasatch front, you can see mostly extension. And over here in western Nevada and eastern California, we have a combination of extension and strike slip events. And so there's oblique slip. So I'll show you some more images that emphasize that in a second. If you were to look at seismic images that are, these are map view of different depth slices beneath western North America. And we'll assume for now that red is hot and blue is cold. That might not be a good assumption. But what you can see is at 25 kilometers depth, here's the Colorado Plateau, here's the Rio Grande Rift, here's the Wasatch Front, here's the eastern side of the Sierra Nevadas. The two areas that are apparently hot at 25 kilometers are associated with where active extension is happening now. So that's pretty interesting. If you go down to 80 kilometers, you see that a much broader area beneath, and this is in the mantle, a much broader area in the Earth's mantle appears to be relatively hotter than the area that's not within the basin and range province. So that's kind of interesting. It seems like basin and range affects, in addition to the crust, it also affects the mantle. So there's a lot of extension happening there. All right, here's a map showing some GPS velocities. And these are all relative to stable North America. So what these points represent, this is a station that's drilled hopefully into bedrock, and these arrows tell you which direction and how fast that station is moving relative to stable North America. And so you can look at what's important is the lengths of the arrows and the changes in the lengths of the arrows. So this right here, the circle represents the uncertainty on the tip of the arrow. So you could draw the arrow in any end of that little circle, and that would be within the uncertainty of measurement. So these ones right here, how fast is that station moving with respect to North America? This one right here, or that one right there.
You're not.
Not very fast at all. In contrast, these down here, you see there's a big change between the length of this arrow right here and these arrows over there, which indicates that there's extension happening between where those two stations are located on the surface. So what you see is generally low velocities over here. That makes sense because it's stable relative to stable North America, not much extension happening relative to North America. But then once you start to get into the basin range, the arrows get longer, and eventually they get really long adjacent to the San Andreas Fault system. But what I'll point out in here, it's consistent with the observations of where the earthquakes are happening. How much of a change in the length of these arrows do you see across much of Nevada? These are all pretty much the same length. But if you compare these ones over here with these ones over here, then you're starting to get changes. And so this is also consistent with most of the extension happening on the east and on the west, because those are where the real changes in the lengths of the arrows occur. Does that make sense to you guys? I'm going to clarify.
And then the northwest is under compression.
No, the northwest. Oh, well, these ones over here. These ones over here. Yeah, these are related to the subduction of the Juan de Fuca plate. And so these are, basically shortening the column right at the plate boundary. Geodesists, they like to make little microplates. And so this is what geodesists look at when they're looking at the extension within the basin or range. They basically, they say, okay, here's this little microplate right here, the Central Great Basin Province, which is moving at 2.8 millimeters per year, roughly as a rigid block relative to stable North America, which means that there's extension within the Eastern Great Basin Province. And then the Sierra Great Valley Province and the San Andreas Fault and Pacific Plate Province, they're all moving to the northwest relative to the Central Great Basin Province, which means that the Western Great Basin Province is accommodating northwestward extension. So there's oblique extension, which is consistent with those strike slip and normal slip focal mechanisms on the earthquakes. I'm just going to skip ahead here. All right, so basically most of the extension is happening over here and over here. Here's a map of where the seismicity has been for, I don't know how long this is on the right side, but probably since the 80s or 70s or something like that. This was generated from the University of Utah group. So you can see that seismicity within the eastern part of the Basin Range and continuing up into the northern Rockies, it kind of has a funky shape, and I'm going to talk about that shape in a second. And you see that in terms of seismic activity in here, there's a lot of smaller earthquakes and not as many big earthquakes, but there are some big ones, and I'm sure you guys have heard of the Hepburn Lake earthquake in 1959, which is magnitude 7.3. And in Idaho, what's closer to home is this 1983 magnitude 6.9 that was adjacent to Bora Peak, which is kind of near Mackey in central Idaho. So some big earthquake events that have happened in this area. We call this the Intermountain seismic belt. The name isn't really that important, but we're finding where the location of seismicity is interesting. And as Mike alluded to, if you go down, I went to school in Arizona, did my graduate work in Arizona, and they don't talk at all about the influence of the Yellowstone hotspot in relation to basin and range extension. That's not even something they think about. But when I came up to Idaho, that's the first thing on people's mind is how extension is related to the Yellowstone hotspot. So I think that's kind of interesting. First order, but what you see are some really cool correlations between, in this diagram right here, which is Rogers and others, there's age getting younger toward the top, and distance from the Yellowstone hotspot, so getting larger from to the west. So these are farther away, those are closer, and you can see generally that extension has gotten younger toward the northeast at a similar rate. This diagram doesn't really show it, but it has gotten younger at a similar rate to the migration of the Yellowstone hotspot or the North American plate relative to the Yellowstone hotspot. So there seems to be a correlation between the location of the Yellowstone hotspot and basin range extension. What you'll also notice is kind of a really interesting pattern here, and that's really good for Pocatello, which is located right here. In Idaho Falls, but not so good for you guys over here in Jackson. But what you see is that there's basically no earthquakes happening within the Snake River Plain. And this is an observation made by several people, particularly in the 80s. And they had some ideas about why that might happen. And their best idea was that here in the middle part of the crust, where you have the Snake River Plain, you have a big stack of basalt. And in the subsurface, they hypothesize, and they think they can see with geophysical data that there is a big, dense intrusion that's associated with all the mafic magnetism from the Yellowstone hotspot. So they hypothesize that the crust actually, in addition to subsiding down in response to that big weight that kind of flexed down in the crust right there, in addition to that, it's strengthened the crust. And so here's some data showing how the crust has subsided down, and so these are some mountain ranges in the east central Idaho, the Beaver Heads, it's all on the Idaho-Montana border, Limhi Range, Lost River Range, and Pioneers. And what this shows, these are contours of basically the extent of tilting adjacent to the Snake River Plain. So what you see over here in the central Limhi Range, 0, so everything's basically flat relative to before Snake River Plain subsidence. But if you go farther to the southern parts of these mountain ranges, they're actually tilted down toward the Snake River Plain. So basically this big dense sill, with all these dense magmatic rocks in the middle part of the crust, they crystallize in there and they flex the plate down, and everything adjacent to it was tilted down toward the Snake River Plain. And people think, and this is an introductory lecture in structural geology, but if you guys remember, perhaps you learned this at one point, we think the upper part of the crust has this shape for its failure. So we call this the Coulomb failure envelope. So in other words, you don't have to know the details of this, but with increasing depth, it's harder, because there's higher confining pressure, it's harder to form fractures. So you go deeper into the earth, there's more pressure preventing those fractures from opening. So with increasing depth, we think the strength increases generally in the upper part of the crust. But as you get deeper, we have a different type of failure mechanism that becomes important. Instead, rocks are behaving by ductile failure, so power law creep in particular. So what that means is that there's an exponential decrease in the strength of the rocks because no longer are they breaking by fracturing, they're actually behaving like goo. So this right here, where you have an increase in strength and then a decrease in strength right there, that's going to be important for what I show on the next diagram. And people think that in these different localities, so in particular look at 3 right here, you can see that if you put a big mafic intrusion into the middle part of the crust, mafic rocks are stronger than rocks that have a lot of quartz in them. So people think that made the middle part of the crust stronger within the Snake River Plain. And that's what caused this lack of seismicity within the Snake River Plain. So here's a view of flexing down towards the Snake River Plain and possible strengthening of the crust associated with that the intrusion that's from the Yellowstone hotspot. Yeah.
Is there a difference in whether it's brittle or flexible? I guess I had thought that there weren't earthquakes because it wasn't brittle, so it wouldn't form a fracture and it would just ooze more.
Yeah, that's a good question. Let me see. So that's a good point. So if you look at, here's a temperature diagrams in here, and the temperature is thought, you can see this goes up right above the hotspot right now. They think it's a pretty high temperature, so high geothermal gradient, right above the hotspot. So they think it's really weak, and they think that actually promotes extension to happen. And so if you look at the locations where active extension is, there's a lot of extension happening right above the Yellowstone hotspot right now, which is probably because the crust is weak. So they don't think that there's as high of a geothermal gradient right here within, you can see a substantially lower geothermal gradient within the Snake River Plain. So they think that as the hotspot passes, it cools, and the reason why there's no seismicity is not because of the high temperature, but because of the stronger material in there.
Okay.
All right, I'm going to talk a little bit more about the Northern Basin Range, and then I'm going to talk about seismic hazards. And once again, I'm not a seismologist, but I'll tell you what I know. All right, so there's also some really interesting data. Some early hypotheses. They said they're wondering why there's these big mountain ranges, big basin range mountain ranges in central Idaho, in the Tetons, and in southeastern Idaho. And they said, okay, well, extension must still be happening in the Snake River Plain, but maybe it's counteracted by every time you open up, you have extension in the crust, it's injected by a dike. So kind of like a mid-ocean ridge, as you accommodate extension, it's just replaced, and so you don't have fundamentally big mountain ranges, basins, and ranges adjacent to it. You just have filling in of the crust as it's being extended. In this paper right here, which is also GPS velocities, what they showed is that the velocities are actually essentially identical as you go along the trend of the Snake River Plain. And this is interesting because it means that there is no extension happening within the Snake River Plain. And so what does that mean if there's no extension happening here and there is extension happening there?
Earthquakes.
Yeah, strike slip faulting. So that's what this paper, this is Suzette Payne, who works for the Idaho National Lab. She's a seismic hazard specialist there. And she hypothesized that this right here, this is just a rigid block that's being extruded out to the southwest. And this suggests that there should be strike slip faults at the boundaries of the Snake River Plain. And there are no strike slip faults at the boundary of the Snake River Plain that we know about. So this is an active research question that one of my students right now is working on. But we're trying to figure out if our hypothesis is that, so if the shape of seismicity is parabolic, so they call this the seismic parabola, if it's parabolic and Yellowstone or North America is migrating toward the southwest, then the shape, the boundary between the Snake River Plain, this rigid province in here, and the stuff adjacent to it, strikes of faults would not necessarily be exactly parallel to the boundaries of the Snake River Plain. They'd be slightly oblique to it. So in other words, here's the Snake River Plain, here's the boundary of where there's no extension happening. So there's actually an area adjacent to the Snake River Plain that also does not have extension. And so we're hypothesizing that perhaps there are strikes of faults, but they're only intermittently active as the North American plate is moving to the southwest. I can talk about that in more detail if you guys are interested, but I don't have a good photo of it or image of it. Okay, I'm going to talk just a little bit about earthquakes, and this is going to be at a pretty introductory level. So here's a diagram from IRIS. So this is why earthquakes occur, because of slip on the fault surface. And I'm sure all you know that earthquakes propagate out from what we call the hypocenter. So the epicenter is the point located directly above where the earthquake nucleated from, so this point, in 3 dimensions. And it turns out, as you guys know, the Earth is old, and many faults that are present within the Earth's crust are no longer active. So, like for example, all those thrust faults that I was talking about earlier today and yesterday, none of those are active anymore. Some of them have been reactivated by normal faults, and that's a whole other discussion. But most of those are no longer active. In case in point, looking in Pocatello, like I said, we're pretty fortunate. There is actually, Pocatello is in a little basement ring half graben, but we don't think that the fault adjacent to Pocatello is active anymore because it's so close to the margin of the Snake River Plain. So that's a good thing for Pocatello. And one of the reasons why you can see it's a basic cross-cutting relationship, you can see this fault in here, it's called the Fort Hall Canyon Fault. It's coming up along here. This side was dropping relative to these mountains in here. And you can see that fault's cut by other faults in here. So and it's also buried by some younger quaternary sediment. So that's good evidence that the fault is not an active fault. All right, and so we classify active faults. Mostly people classify them as have known activity within the last 10,000 years. So this would not be classified as an active fault. And everyone always asks me, can we predict earthquakes? Does this sequence of earthquakes mean that there's a bigger one to come? We can predict earthquakes. We know that there's going to be earthquakes all along this belt in here within the next 10,000 years. But whether they're going to happen tomorrow or in 9,000 years, we don't necessarily know. So it's a little bit dissatisfying. But I'm going to talk in a little more detail. Have you guys heard of this earthquake that occurred a couple weeks ago in southeast Idaho? It's near Soda Springs. And so I've been, I'm not a seismologist, like I said, but there's no seismologists in eastern Idaho. So when there's an earthquake, the media call me and they want me to say something to them about the earthquakes. And so I've learned a lot about the earthquakes in this part of the world. But I'm going to talk a little bit about this earthquake near Soda Springs and what we've learned. And some of this stuff is, a lot of this is from the USGS or from the University of Utah Seismograph Network. So I will give credit to them. This is not my own personal research per se. But some of this is applicable, and if you guys are interested and you didn't know how some of this works, you can definitely go on the earthquake.usgs.gov website and you can see all these same exact plots, see where the shaking is. So like there was an earthquake last year in the Gros Ventre. I don't know, has there been any more recently than that? I know there was like a magnitude 4.3 or something like that. You guys remember? Yeah. So you could go on there and you could see a shake map. So this shows you what the colors indicate what sort of shaking intensity happened with distance from the earthquake. And you can see from this earthquake in Soda Springs, which is a magnitude 5.3, you can see that right at the epicenter, so the location above where the earthquake occurred in the subsurface, you can see that it's kind of getting into this kind of bluish green color, perhaps over here into this a little bit. And the perceived shaking from that intensity would be moderate shaking. And the expected potential damage would be very light potential damage. And so this is kind of a snapshot of what happened a couple weeks ago. if you look at, so I know unfortunately this is a Google Earth view, oblique view of a geologic map from where all the earthquakes happen. And I know that you can't see them very well because they're orange, but I couldn't change the colors without individually changing the colors on them in Google Earth, so I didn't. But what you can see, it's just east of Soda Springs. There were a lot of earthquakes. There were over 350 earthquakes that were above a magnitude 2.5 or something like that, and thousands of earthquakes, over 3,000 earthquakes that were much lower intensity than that. So a lot of seismicity. And just as an example of this concept right here, what we call shaking amplification. What happens is that in hard rock, seismic waves are traveling at relatively high velocity, and when those hit relatively unconsolidated sediments, they're forced to travel at a lower velocity and therefore increase the amplitude of the waves that are traveling within that substrate. So it turns out most cities are built in basins, and that's a bad thing for earthquakes, and that's probably why this magnitude 7.1 in Mexico that happened yesterday, I think, or maybe it was today. When was that? Yesterday?
Yesterday.
Okay, yeah, it's probably why, because Mexico is built on this big drained lake, and so there's unconsolidated sediments between Mexico City, so that's a bad thing for earthquake shaking. And I'll just put up this map, so this is from the 5.3. You can see the map, the contours of the shaking intensity, and you see how this basin down here just basically funnel the more intense shaking down toward the south, toward Bear Lake. And so this is a view of how that shaking amplification looks in reality. And in contrast, in this bedrock over here, the shaking was not nearly as high with the shorter distance from the earthquake, which is pretty cool. Well, pretty cool if you're a geologist. Not if they're happening right by your house. All right, so here's a summary of this Soda Springs seismicity. So there are actually quite a lot of magnitude 4 earthquakes, over 22 that were greater than magnitude 4. 310 reported by the USGS, and the media called me and they said, the Utah Seismic Network, they have 309, but the USGS, they have 311. Why are there? I was like, oh man. And so the story the next day was, it was all about why there's a discrepancy in the earthquakes reported. But it turns out that there were over 3,000 earthquakes, and most of them were aftershocks associated with this main magnitude 5.3 event. But it's an extraordinarily large number of aftershocks for a small earthquake like that. And there's some really interesting things, and all these images are from the University of Utah. But if you look at the distribution of seismicity, and so each dot, and this will loop back around, each dot is white, and then when the earthquake happened, it goes red, and then as it gets older and older, it goes from blue to black. And so you can see that, do you see any patterns?
North to south.
Yeah, so generally, their seismicity migrated from the north to the south, which is kind of interesting. You probably don't care about the temporary stations they deployed, but there was a map of it if you're interested. There was some preliminary synthetic aperture radar interferometry data. So that's a complicated way of saying satellites are circling around and measuring detailed surface elevations. And then when they circle back a second time, they can see how the surface elevation may have changed slightly. And there was some preliminary information that suggested on the 10th of September that there was about 3 centimeters of subsidence near where the earthquakes occurred. And so that was pretty interesting. That's quite a lot of subsidence actually for an earthquake with a relatively small magnitude like that. Getting back to looking at some more focal mechanisms, in addition to the north-south migration of seismicity, there's also an interesting pattern, and I just did screen captures on the USGS website to plot these up. But what you see is that the focal mechanisms in the north, what kind of faults are these associated with?
Extension.
Yeah, those are extensional focal mechanisms, so normal faults. What about these ones to the south? Yeah, more strike slip components to the ones in the south. So that's pretty interesting. I don't know why it is, but it tells us something about probably 2 faults that seismicity is occurring along, and these early earthquakes are triggering displacement on this. I think this southward migration, it's a little dangerous to tell the media that this is that is kind of a zippering effect. Because you all know what happens when the zipper, you imagine, have you guys seen the movie Santa Paradise? I haven't actually seen it, but people imagine this whole crust is just going to rip apart and everyone's going to fall into it or something. But it is kind of like a zipper. So I'm not sure if there's increasing obliquity on the slip surface as you go far to the south, or maybe there's two faults that are active, at least two faults that are active. You can see kind of the plot of the magnitude and the type of focal mechanism. This is from the USGS site. You can see initially they're extensional, they become more oblique slip through time, and they generally decrease in magnitude. So that's pretty interesting. And if you look at the cumulative moment exponent, and to be honest, I don't know what that means in detail, but it shows you that the amount of energy that's released has been decreasing through time, basically. So it has this shape on here. So that's good because it suggests that the energy is dissipating and there's probably dying out of seismicity associated with that first event, rather than the scenario that the meteorologists ask me when they call me is, does this mean that there's going to be a magnitude 7.1 coming tomorrow? I don't know. It's possible, but because earthquakes are known to trigger other earthquakes.
I have a double question. How deep was Soda Springs?
How deep were the earthquakes? That's a great introduction to the next speaker. So if you look at map view, here's the location of earthquakes. Here's age. You can see they're going to the south. If you look on an A to A prime plot, you don't see anything too useful, I don't think. But if you look at B to B prime, so this is roughly perpendicular to the focal mechanisms, you can see that the maximum depth was about 18 kilometers, but most of them were between 14 and 2 kilometers depth. The largest event, the magnitude 5.3, was 13.7 kilometers. That's an early depth estimate.
Okay, my second part is, if they can tell how deep it was, can they tell how much displacement there was right at the point where it slipped?
I think so, but I don't know how they do that, to be honest.
Okay, they have to surmise or hypothesize something.
Is that the bottom of the Cambrian sediments there?
I don't know. I don't think
Actually, that makes sense. That's a snake river.
it might be. It might be around there. I'm not sure because there is a big thrust fault. It turns out right here. This is called the Paris-Willard thrust, and then the Meade thrust is kind of over here. But I'm not sure. This is this depth down here, 15 kilometers, is kind of the maximum depth of earthquakes in the basin of range. Why do you think that is?
That's where the bedrock is.
That's where the boundary between the brittle rock and the ductile rock. It doesn't fracture below about 15 kilometers. So these depths are pretty standard for where the earthquakes are occurring because you don't expect fracture to happen below that. So I don't think I answered your question, but I don't know. It's the bottom line.
Just the fact that they don't say anything about it would tell me that they can't figure it out.
Yeah, well, this is not at the top of their priority list.
Well, like Mexico, I mean,
Yeah.
can they say, well, it went 30 feet or?
Yeah, they can for those big earthquakes.
Oh, okay.
Yeah, they can. They can plot out in detail what the slip distribution was on the surface and that kind of thing. But I don't, to be honest, I don't know the details of how they do that. So if you can, kind of squint and tilt your head a little bit, you might be able to see that maybe they have a generally eastward dip to them. And so maybe they're occurring on an east dipping fault. And that's actually my best guess as to which fault they're occurring on. Because if you zoom in on this area right here, which you can't really see here, this is just a USGS quaternion fault map, you can see there's a fault mapped just southeast of Soda Springs, and this is called the Western Bear Lake Fault. And so they thought that there was an active fault there, but they didn't really know much about it. It was dotted and it was black, which means they didn't know how old it was and they didn't know where it was. But
Does the Wasatch Fault zone go up that far?
No, the Wasatch Fault continues into fault zone, continues down into southern Idaho, and then it basically it starts to step over mostly toward the east. So the big faults in here, the Bear Lake faults, those are big whopper faults. Those are, I think it's the Bear Lake Fault, and I have something on here about the Bear Lake Fault, they think that from the data they have, they think there's a potential for a magnitude 7.3, which is a big one. And that's on the basis of a couple of fault trenches that were dug into the eastern Bear Lake Fault down there, and that was by Jim McAlpin and some of his colleagues. And so you can see that on here, this is kind of up in this range right here, so you would expect violent shaking and heavy potential damage. But there's not a lot of people that live down there, and that's why they haven't plotted up the slip distribution on these normal faults from the magnitude 5.3. They're much more concerned with the Wasatch Front. So here's some probabilities. Actually, this really interesting study from the Wasatch Front that came out last year. And what they did is very statistically robust, and I don't understand the details of what they did, to be honest with you, but what they did is they tried to quantify the probability that each of these different segments would produce an earthquake of a particular magnitude, and then they summed all of these probabilities to say what the likelihood that somewhere near the Wasatch Front would have an earthquake of a certain magnitude. And they said there's a 57% probability that there would be a magnitude 6.0 or above within the next 50 years. That's high. And they said that there's a 43% probability that there would be a magnitude 6.75 or higher within the next 50 years. So that's also pretty high. So that's just on any of these faults in here. And each one of these faults contributes a little bit to that cumulative probability. So you can see on the eastern Bear Lake Fault, they think there's a 6.3% chance that there would be a magnitude 6.75 or greater, and a 7.4% chance that there would be a magnitude 6.0 or greater.
So can you tell, I can't read it from here, our little fault over there in Wyoming? The one,
This is the Rock Creek Fault, and this one.
that's the one that goes through Teton Village, yeah?
No, this is actually much farther south from here.
Oh.
But I do have a plot of the. Now I got this. I'm not sure if this is the most up-to-date thing, and you guys might know more about this than I do. But I just searched on Google for Teton fault rupture scenario, and this is what it does from USGS. They have an idea of what the maximum earthquake would be along that fault, and then they do a scenario to show what kind of shaking you might expect. And so what they have here. So it doesn't look good for Jackson, as you probably know, so let's hope it doesn't happen, but you can see it's red in here, so that's also, they think there's a possibility for a magnitude 7.2 and violent shaking and heavy damage. And I'm sure they're going to revise this because they're doing, some of you went out to see the active fault trench that they were digging for the last couple of weeks. And they found, from what I heard, they found evidence of 3 rupture events. And so that's good because that means they'll probably be able to quantify. If they can get good material to date, that means they'll be able to quantify what the recurrence interval is and perhaps the likelihood of rupture along that fault. So that's pretty much all I have. And if you guys, so that wasn't really, most of my research, but hopefully it was interesting to you.
Right.
Thinking about the basin range and seismic hazards and that kind of stuff.
Yeah, no, that's great.
Yeah.
Great.
You guys have any questions?
So have you published your thesis for the first
Yeah.
part of the talk?
Yeah, so the Argentina part was my PhD dissertation, and the North America stuff is that's something I'm just getting started and just got this proposal funded this summer. So we have big field season planned for next year and the year after that. So we already have some preliminary data from the thrust belt, but we don't, we're still kind of figuring things out, early stages. But the stuff from South America is all published. So there's several papers. 2012, 2013, a couple of 2015.
What kind of reaction have you gotten?
There's various reactions. Some people are like, well, duh, and some people are like, well, I don't. There's some crust belt geologists that just refuse to think that there's any sort of, they refuse to believe this reactivation idea that faults prefer to be reactivated rather than forming new faults. And I think it mainly comes from their work in these relatively undeformed parts of the full thrust belt where they see new thrusts forming within the stratigraphy. So some people are opposed to it.
Yes.
I haven't gone out in a publication yet and said flat slab subduction does not cause thick skin shortening. So we'll see what happens when I say that. But I do think that there's good evidence that there's not necessarily a cause and effect link between the two different, shallow subduction and the structural style. So that's something I'm building up toward incrementally. So that's something I've learned already as an early career faculty member. You can't just go out and say, you gotta kind of eke your way up to it.
I'd like to comment on that. Unlike most scientists, he has all his papers on his webpage, and you can read the PDFs, you can see all this stuff, and that's not the norm,
Yeah.
unfortunately. So I'm happy to see that.
I'm not allowed to do that for some of those. So
You're not allowed to, because of.
Yeah, the copyright.
They should-
Copyrights.
The
Somebody
scientific
else-
organizations don't believe in
of these
communicating
organizations.
science.
Right, so how do you get
That is gonna
around
change
that
that.
copyright?
It is changing.
yeah, AGU, their policy now is that within the first year, it's not open access, but then after the first year, it will become open access. So that's great. And then GSA, I don't remember the details, but they're transitioning to a primarily open access model for their publications.
Player
But
after theirs.
there's other journals like Elsevier and that kind of stuff, and I think they're a long ways off from doing something like that. But we'll see. Maybe the dominoes will fall.
Just to make you feel a little better, the Palisade Reservoir, which is to the southwest of Jackson Hole, the dam is built to sustain a credible 7.2 magnitude earthquake.
But it's below.
Yeah, that's what we hear about that.
How about this one?
Rockefeller's care. I mean, you do care, but not that much, right?
The faults down by Afton, Wyoming, have had 2 episodes of 7.2, 7.3 faulting in the last 10,000 years. So it's, in case you go fishing on the lower snake, check your horoscope for earthquakes.